Hello and welcome. In this video, we will see how to predict the quality of wine using advanced R programming. The task covers exploring the data, transforming it, building models, and summarizing the analysis. The dataset we are working with consists of 6 variables. 5 of these variables are independent, representing the physiochemical properties of the wine, such as citric acid, chloride, and alcohol. The dependent variable is the quality of wine, which reflects the wine's overall score. In total, the dataset includes 1599 records. This is a 5-point summary of the dataset, which provides an overview of the dataset by highlighting the minimum maximum values and the 3 quartile values of the variables. Before performing any analysis, a seed based on my roll number was set to ensure the reproducibility of the results. From the dataset, 400 records were selected for exploratory data analysis. As a part of EDA, scatter plots, histograms, box plots, and correlation metrics were generated to visualize the relationship. From the histogram and box plots of citric acid, we can observe that the distribution is right skewed. Chlorides is highly right skewed with presence of outliers in the right side. Total sulfur dioxide is also right skewed with the presence of outliers. pH has an approximately normal distribution with almost equal number of outliers on either side. Alcohol is slightly right skewed with moderate levels dominating. The target variable is discrete, ranging from 3 to 8, with most of the ratings lying between 5 and 6. From the correlation metrics, we can observe that the citric acid shows a positive correlation, suggesting quality improves as citric acid increases. Chlorides and total sulfur dioxide shows a moderate negative correlation, indicating that higher levels of these can reduce the quality. pH displays a negligible correlation, indicating almost no relationship with quality. Alcohol has the strongest positive correlation, highlighting its significant impact on the quality. Calculated the skewness of the variables, and the calculations are tabulated here. It also reveals that chlorides are highly skewed and the rest of them are moderately right skewed. I created a function to identify the best transformation for a variable. It calculates the skewness of the original data, applies transformation like log, square root, inverse, and polynomial, and computes their skewness values. By comparing these, it identifies the transformation with the skewness closest to 0, ensuring a more normal distribution. This function outputs the best transformation and its corresponding skewness, streamlining the whole process of selecting an optimal adjustment for the data. For example, when applied to citric acid, it can be seen from the output that the transformations were applied. From the various transformations, the function chose the polynomial transformation with degree 0.75. Similarly, all other transformations were obtained. The results of all transformations are tabulated on the screen. We can observe drastic improvement in chlorides from 7 to 0.6, which underwent inverse transformation. Post-transformations, z-score normalization was applied to the variables and the processed data is stored in a text file for further analysis and data modeling. In order to build the models, these 4 aggregation functions were used, which were defined in a file provided along with the assignment. These functions were fed the processed data and the output is captured into the respective text files. The screenshot of respective outputs obtained through these 4 functions are shown on the screen. Each file contains metrics like RMSE, average absolute error, Pearson correlation, Spearman correlation, and weight of each model. For better understanding, these metrics are tabulated for comparison. We can observe that the weighted arithmetic mean has outperformed all the other 3 models by giving least errors and good correlation. Therefore, weighted arithmetic mean is selected as the best model for further analysis. For the prediction part of the assignment, the provided input values were transformed using the same transformations which were applied earlier to the data prior modeling. Also, the pH value has been dropped as it was not considered during the modeling also. In order to get the prediction of these input values, the weights of the selected model and the transformed input values were used to calculate weighted arithmetic mean, and quality was predicted by calculating inverse Z transform. The result obtained are shown on the screen. The predicted value of quality is 5. While weighted arithmetic mean offers a straightforward way to predict wine quality by weighing features, it assumes linearity and proportional contributions, which may not fully capture the complexities of wine quality. The analysis has been successful in all the provided tasks. Weighted arithmetic mean model emerged as the best model, which predicted a reasonable quality score of 5, which lies within the range of 3 to 8.